Good evening, everyone. Myself, Vikash Kumar. I am a second year BS Chemical student. So, I am a representative of Group 10. We will be discussing about, so, so we will be discussing about activity speaker detection. So, we will discuss this by considering two data set available here. First will be AVA ASD, which was released by Google, and second was Columbia Speaking Dataset, which was released by Columbia University, US. So we will be using these data sets to understand the underlying features, and also we will discuss what are the contributions that we have done, what are our analysis, what are the metrics scores that we have got. We will discuss this in details. So let's start with the introduction of AVA dataset. So AVA dataset consists of Hollywood movies, which consist of 120 videos for training and 33 videos for validation. And it was released by Google in 2019. And it would be our primary and training evolution dataset, which we had worked, and we have used Columbia dataset for as the inference. We haven't changed our model anything. We just used for Columbia. Okay. So this is the binary level prediction dataset. We have to predict for every frame either it is speaking or not speaking. Okay, basically given a video containing multiple visual faces, and we have to determine which person is speaking at each moment in time. The system receives synchronized audio and video as input and must produce a per frame binary level for every visual face, speaking or not speaking. Fundamental component in this video. So basically, it is very mostly used, can be used in video conferencing where you want to understand and know which person has spoken, so that you can understand. Okay, this person has spoken, and lecture hall you can, yeah, you can see which person has asked out, whatever you can see. So it could be very important for real world scenarios. Okay, let's talk about Columbia dataset. The Columbia dataset consists of 87-minute video, which are very high quality videos. So it is also very useful for benchmarking the activity speaking detection models. So here there are five panelists in this video. You can video and Columbia active speaker detection. So their names are Bell, Ball, Lip, Long, Sick. So basically, in 35 minute an innovative clip from 87-minute recording at Columbia University with a camera angle which varies and also focusing on 2 to 3% once. A contains continuous conversation with short overlaps during the speaker changes. The primary metric that we are using here is F1 score, which is computed by frame score against the ground to speaker levels. So let's discuss the state of the art score over on this AVA ASD dataset. So it is achieved by Loconet, which is 95.2%, and it was also published in the CVPR in 2024. So the reference of the paper has been mentioned here. Our model has got accuracy of 93.52%, which is also a modified version of DocNet, so which was published in ACM Multimedia 2021, and it has uh, uh, achieved a significant margin over the DocNet. Our experimental model also achieves F1 score of 71.25% using temporal transformer model on the Columbia Active Speaker dataset. Okay, so let's say talk about the novel contribution that we have done. The first one is TalkNet NCE, the contestive audio visual loss. So the earlier models that we are using, it only wants to understand either it is speaking or not. Okay. But what we are doing, we are enforcing our model or making constraint so that it could understand that audio and visual embedding should be more similar because it should be coming from same person. Okay. So then it computes the cross-model contestive loss. Okay. So basically, suppose there's a pair of A1 V1. So A1 is the audio feature coming from the person one and visual feature coming from the person one. And the second pair is A1 V2. The audio comes from the person A1 and visual features coming from the person V2. So this pair considered to be negative for this purpose because we want similarity here. For the similarity, we are using a similarity-based metric technique, which is called cosine similarity, and we are scaling this cosine similarity with a scaling factor temperature here. So with setting the temperature as 0.07, the AVMAP score that we have got is 68.25%, and the Columbia score of 67.11%, and we have got domain drop of 1.14 pp. So this contrastive loss reinforces the transformer to learn intrinsic speaking features rather than co-occurrence patterns. So this generalization behavior is almost identical to transformer alone. Okay. The second one is correlation, CIR, correlation independence regularization. So we design and implement a novel training regulation that directly penalizes interface prediction. So what we have seen in our analysis that there is an interface prediction, interface dependency. So like this also occurred because it is the data set contains the Hollywood movies where if a person speaks A, the person B also has to speak. So suppose hero comments something or the villain also has to turn his back and say something. So there is a dependency over here. The model has learned. Okay, if two faces are in the picture, it might the second person might be speaking to him. So what we have done to reduce this, like we have computed the correlation, Pearson correlation between the speaking scores of person A and speaking scores of person B. And by this uh, computing the correlation, we are using this in a loss function as a constraint for this to reduce this interdependency. So the total loss function becomes loss audiovisual plus zero point 0.5 into loss visual plus lambda into correlation factor. And we have trained three variants of lambda 0.05, 0.10, and 0.20 in parallel GPU because we have GPU cluster in IIT, and we are using that. So we can train on these. So different variants were trained. So let's see result on CIR 0.05. We have got 90.38% MBP score, and Columbia we have got 65.51 score, which drops 24.87 APP. And for 0.10 on AVA we have got 88.7%. So this we have seen there's a drop in Columbia. There's also drop in AVA. We'll also explain the reason behind this in next slides. So CIR reduces the multi-phase model's domain drop from 18.50 to 20.6, marginal improvement. Okay. So the finding is that explicitly penalizing the correlation is insufficient. So we have to find some root causes for this. Let's see next. IRM, invariant risk minimization, negative results. Okay, we don't get any positive results. So we applied IRM. What is this IRM? So I have told you that there is the interface dependency. So first, what we are doing, we are creating separate environments for each of the settings. If single face is there, we are getting environment one. If more than one face, environment two. Then the both are passed to the same encoder and same classifier. And what we got iron gradient penalty, so which is equal to square of gradient loss with respect to dummy scale multiplier, and which is computed separately for each environment. Okay. In practice, so AVA dataset composition problem with only 13 single phase segments, and out of 1786, the INM penalty was computed on nearly empty batches, was effectively zero for training. The result, the AVMAP was 90.88%, the Columbia F1 63.73, and the score is very less because the Columbia baseline score 66.24%. IRM failed because it needs a very balanced environment. So here there is imbalanced condition between single phase and multiple phases. I also saw a pie chart in the next slide. So that tells you about there is a imbalance. So CAMIB, causal multi-model information bottleneck. So it's a negative result. So what we did here, we use variational architecture that splits our 120 dimensional input that we have got from fusion of in audio plus visual part. Okay. So what we are thinking that we are splitting into two halves, 64 dimension, 64 dimension, 64 dimension for causal one. So what are causal? So properties are those which captures lip movement, lip sync, mouth opening, closing. Okay, these are causal. And shortcut is like understanding the interface correlation, variance of these, and orthogonality constant. This is what we have seen. So it uses a variational encoder with KL divergence regularization. And what we have seen that we have achieved 64.49% Columbia, which is also poor than baseline because we need more than this. There is the architecture collapse due to the discriminative single signal rather than distinguishing causal and spurious components. Okay, so the bottleneck compressed output score ranges from minus 4.9 to plus 2.7 inch or to a much a narrower minus 0.42. There's a decrease in the output score that you can see. That's squeezed. Okay, so SCSN, the scene condition calibration. So we use clip-based VIT model to encode video frames for both AVA validation clips and Columbia test video to a 512 dimension scene embeddings. We trained our MLP that takes clip scene embeddings plus raw ASD scores for 50 frame, and then the network learns that certain visual scene context correlate with certain optimal calibration. So on Columbia, the SCSN achieved 67.1% F1 score versus 66.2 for baseline score. So there is a very little bit improvement, 0.87. So the contribution is that we are using the vision language based embeddings as a condition for ASD score calibration rather than using large accuracy improvement. Okay, so let's give you a brief and more concise information of input data flow. Okay, we are earlier we talk about the different techniques that we have employed. I will explain you the input data flow. So we it consists of two modalities here. So the first modality is your video part, and second one is the audio. For the audio, there's only so let's discuss about audio first. So the generally the raw audio is really stored as .wav files, which is sampled at a frequency of 16,000 hertz, which is very standard for speech processing techniques. And after this, we are adding noise because dataset is very intended to be cinematic from the Bollywood settings. We want to add noise because in real world scenario, there might be noises coming from the your surrounding, your chit chatting someone, the fan sound, the construction sound. These are the sounds always there, which overlaps with the speech. That's why we have used the augmentation here, the noise adding -5 to plus dB. Then MFCC extraction. So we humans perceive sound differently. We don't perceive sound as linearly. We perceive sound as logarithmically. We perceive sound as something. We perceive sound as like we perceive sound as logarithmically. So what MFCC does, it extracts the features which are very relevant to us. Okay. It also extracts the certain coefficients do why short like fast Fourier transformation by using pre-emphasis. These are the mathematical functions that they use for feature extraction. After this, we are using padding. So padding, what it does, it pads the audio length because audio length we want to be consistent. If there is no consistency, there will be difficulty for us. So we need padding. After this, audio output. And second is the visual processing. We did face.jpg. Basically, we extract frames from the video. After this extracting of frames from the video, we then goes to pre-process. We resize our frames to 112 by 112 pixel size. And after this, what we do, we convert this to from RGB image to BGR. Sorry, RGB image to grayscale. Why? Because we only want to understand the lip movement, mouth opening. Okay, we don't want to understand the skin color, the lightning process. By doing this, we are reducing the model complexity. We are reducing our computational complexity. Okay, then after this visual augmentation, we are using some augmentation technique like flipping, cropping, rotating. Then stack frames, say num frames, 112 by 112. Then visual output. Then, okay, this is what we have explained earlier, diagram. So resizing it to 112 by 112 pixel. Then only the face region is being used, no body, no background, no other people has been used. The grayscale conversion, face crops convert to grayscale. Okay, I will explain. The normalization, so these are being normalized to data specific mean 0.461 and 0.1688. And the formula being used here is, okay, same thing. So, okay, I'll explain this same. Okay. So let's understand the architecture. So last case architecture that we have discussed. So visual front end. So the visual front end part generally contains information about our frames. So after this, what we do here is normalization. We normalize with the mean statistics and the standard deviation that we have been provided over here. The mean is used 0.4160 and the standard deviation as 0.1688. After this, we use 3D convolution blocks. The question might be why we are using 3D convolution. Because 3D convolution understands the temporal moment also. We don't want to understand all of the spatial features. We do want to understand how these spatial features evolves over time. So we also want to understand space versus time understanding. That's why we are using 3D convolution. And also we are using max-pool 3D. So max-pool 3D is being used to reduce the computational cost and also the memory structure. Okay, that's why we are using. And second is convolution block. Same thing, the convolution block 2, convolution block 3, and adaptive mix pool 2. For audio front end, we are using audio input and then we are on skews plus transpose. So make it in a proper fashion so that it can be used for frequency versus time access and convolution. So convolution 2D, we want to understand the speech features, speech energy. We want to understand the phenome levels of sound, the elements sounds. So that's why we are using frequency versus time, and we are using 2D signal for that purpose. And that purpose, we are using BN, the batch normalization plus RELU. So batch normalization is being used here for reducing the need for internal covariate shift. They would be no to reduce the internal covariate shift. Okay, so the same thing about the block 2 max pool over this mean over frequency dimension. Then concatenation. So we are concatenating these 256 dimensions coming from the audio part and the coming from the video part. And after this, we will be getting the dimension of the channel dimension will be 512. Then we are using channel attention gate. So we want to understand which features give a high impact, which features give a low impact. So basically, we are re-weighting to this according to this. So basically, one particular feature can give us information about person speaking or not speaking. We will give more weights to that. So you can think like if the audio is ambiguous, you want video to be boosting. If video is boosted, you want audio to be boosted. After this detector module to understand the temporal moment and the correlation between the how evaluation of the frames or the video parts or the audio. Then after this, we are using dropout so to prevent co-adaptation between neurons so that each neuron can learn independently. So GRU forward and GRU backward techniques are being used here. So GRU techniques are used. The question is why not use standard RNNs? The standard RNNs is not being used because due to the vanishing gradient problem. So vanishing gradient problem is caused because the gradients are being multiplied again and again, and they are very small. So GRU, so greater recurrent unit. So it contains a reset gate and update gate. So reset gate basically and update gates are used. So they learn which features to store and which features to discard. Okay, it's also good for the long horizontal dependency models. So GRU forward model learns the before the basically learns the past sequences and the GRU backward learns the present information and concatenation. And same as the attention gate, it learns the temporal movement between the features of audio which are being mixed, which has been after the attention gate. Then this we are reshaping into 256 dimension, and this separates into two parts. The 256 dimensions is being sent to projected to a linear projection from 256 to 128, and we get output as audio visual part. And linear part we get also visual only head and visual embeddings. Okay. So basically I have explained all of these in our presentation. So this is the full results table. So the highest that MEP scooter we have got for last capacity is 93.52%, and this 71.25% on F1 score of Columbia. So this is the statistical analysis of Columbia speaker dataset. So you can see here the number of faces present in a frames varies. So the maximum is for the generally two faces are always present in a frame. So 51,000 are those frames where two persons are always there. Then 21,000 or 749 are those frames which only consist one person. And same with this three faces in frame. Now we'll see that the scores of the TalkNet, LRSD, and Transformer multi-phase in FCI on the AVA active speaker. And this pie chart shows that only 20.4% the frames are those which consist of one person, and the rest 79.6% shows that more than one person faces are present in a frame. So this is the architecture of a transformer temporal Columbia dataset. This is nearly same, but there are some minor changes like the channel size is very decreased to 128. You can see the audio input is the audio encoder is being used here same. So the audio encoder we have used same. You can see the channel size increases from 1 to 32 with the frequency versus time convolution with the same techniques that we have used in large capacity. Then say 32 to 64 channel. After this 64 to 128 and a global pool plus reshape. Same with the visual part. We have used the 3D convolution and also the max pool 3D. Then channel increase to 32, then 32 to 64, and 64 to 128, then adaptive pool. Then we are concatenating this visual. Then channel attention, the convolution 1D plus batch normalization plus sigmoid. So the same thing that I have explained, we want to understand the features which are very important to us, and we want to reweight them based on information. So basically, again, like when audio is ambiguous, the visual features will be boosted. And visuals are ambiguous, the audio should be boosted. The same thing general attention should learn. And temporal detectors should understand a temporal temporal understanding within the fused audio and video uh, uh, parameters or representation. Then after this, we are using dropout to prevent any co-adaptation. Then linear projection from 256 to 128. Then after this, we are using transformer encoder, which is a four head multi-head attention. So these four head learns their specific different characteristic of some of these same features, which has been predicted to 128. It will learn differently and they will be mixed so that we can use after this. So output ASB that we have seen for audiovisual part, and this is for audiovisual part. So Columbia, same thing I have explained earlier. So the paradox, the better AV MAP doesn't guarantee a better real performance. So Chestnut achieves 92.15% AV MAP, but only 62.51% in Columbia F1. So because there is a very significant gap here for a data set. One is very cinematic, one is very realistic. So you can see this gap. So LRASD achieves 94.1% ABMAP, but only 66.24% on Columbia F1. Okay, the transformer variant achieves the 70.27% AVMAP, very less, and 71.2% on Columbia, highest in table. So more parameters make generalization here the worst. So basically, the extra capacity is being used to memorize the AVA specific patterns, not learning the universal speech acoustics. So I have to tell about the co-occurrence correlation analysis. Co-occurrence on same occurrence of both. So Hollywood movies have a very statistical structure. Conversations are professionally edited. When person A speaks, the person B also has to speak on the screen. The audio-visual co-occurrence patterns reflect deliberate cinematic composition, not natural conversation. Okay, so basically a person like in a Hollywood data set, when When a hero says something or comments about villain has to respond. This is the same thing. The audio-visual co-occurrence patterns reflect deliberate cinematic composition, not natural conversation. So more models trained on this data learn editing rhythm, not speech physics. So you can see the Pearson correlation coefficients uh, doing simultaneous space prediction with ABA validation set. So the multi-phase mean gets 0.59 correlation factor, and tension context gets 0.34, and large complexity get very less 0.02 or near zero. So the multi-phase models learns how to get when person A is speaking, the person B is also speaking and gets a higher prediction score. Not because B is speaking, but because model learned their co-occurrence from movie editing. This shortcut boosts ABA performance, but is completely absent in Columbia's naturalistic discussion. Why? Because the most people are visual simultaneous in Colombia. So the statistical relationship model learned from ABA simply doesn't exist in Colombia. And this is the a diagram for the Pearson correlation analysis. You can see highest for multi-phase mean, and for the this is for second highest in the attention context in CIR 0.2. Then these are the very less. So how the phase count is important for us. We have seen an AVA on our the Colombia. The most of the frames which consist of two phases are like 51%. Now, of course, 80% of these frames are getting more than two phases in a frame. So as the number of frame size, as number of person in a frame increases, there is a reduction in the metric score, either it is MFP or FN score. So you can see for one phase, the metric score is nearly 96 or 95, 97. Then after this 84 and here this. Then also for two phases, you can see 85, 94 or 93. But when you come to three phases, you can see 84, 85 or 74. Okay, this is very nearly it. The multi-phase model degrades catastrophically because as the phase count increases from 1 to 3, we can see 84.77 to 43.08%. So it has learned to predict based on presence of all the phases. And when many phases are present simultaneously, it becomes confused. The transformer shows consistently slower performance across all phase counts, but uniform degradation. You can see also here from here. So the multi-phase 84.77 to 43. Oh, this is a huge gap, 40% gap. Transformer 75.76, 65.56, and 56.25. There is a gap, consistent gap, 10%, 10%. This is what we have seen. So conclusion, our model a large capacity has achieved 93.5% on the modified topnet base architecture and gets a significant margin. And our experimentation achieved F1 score of 71.25% using temporal transform model. Okay. Then the weighted analysis of how a number of phases affect mean precision, average precision, and F1 score. We are understanding the co-occurrence correlation pattern ABA ASD. And these are the references you can see and we have seen, we have used for our research process. Uh, Thank you for watching. Thank you for your time.